My apologies. Okay. All right. So today, what we're going to talk about is make sure I turn this phone off so we don't get any disruptions. Okay. So for today, we're going to talk about something called tries. All right. Now we've got a couple of videos to watch to help us with the understanding what they are. They're used for they're used for processing strings, string processing. Um, oh, there was one other thing. Oh, and also I've been in contact with the professor that is the author of these slides, and he's supposed to have a, you know, he and I are possibly going to have a meeting on Thursday, and to talk about some of the things. But he said that he's not been authorized yet to release the videos. He's made videos with these lectures. I can't wait to get a hold of them. Once we get them, once he's authorized to release them, I'm going to put them on my GitHub. I'm sorry, my Google Drive, so you guys can have them. You have enough, right? You've got enough information. I think we've covered that, for like 2 weeks, right? 2 weeks solid. We covered those range minimum queries problems and different solutions. So I feel like you guys are in pretty good shape. You should have everything you need. Okay. All right. So for the tries, let me go ahead and turn on screen sharing. Now, what I need to know, we're going to watch a couple of videos. Okay. And then we're going to jump into our slide deck that we have, and then see what was in the videos, if it helps us to understand those slides better, which it does, right? I've already looked at it. So let's first data tries. Okay. Now what I need to know, guys, if you can't hear this very well, I can plug in another speaker to help with this, but let me know if this is not loud enough.
Hi, I'm Dale Lack McDowell, author of Captain Coding Universe.
Is that loud enough?
Yeah.
Okay.
Today I'm going to talk about tries. This isn't something CS students might have spent that much time on in school, but it's really, really important for interviews.
A trie is a data structure that is actually a type of tree, but it's often used to store characters. And the way that it works is each node might store just a character as its data. But then if we look at the path from the root down to that node, that node is really representing a word or a part of a word.
Okay, let me pause here for a moment, guys. So what I want you to look at is that we have a marker. Basically, it's a null, right? So you keep going, and say from the root node here, you'll see here's car, right? And she's kind of written off here off to the side, what these would spell out. But a complete word is whenever you traverse until you find a null. Okay, so here's a complete word, car. And then if you start from here with the C on this branch, here's a complete word called cot, C-O-T, right? C-O-T. And then here's the null for that. But then this one's actually extended to cots and null. And then going back over here, this R, the right-hand side of it, is extended as well. And then it is a full word, or you can make the plural of it. And there's an asterisk down here. The little, the closed captioning is blocking it. Let me see if I can turn this off. There we go. So if you look through here, right, we've stored all these words as a try. Now, you'll notice something here. Notice the one thing that's different is that we actually have a node now that has 3 branches. We didn't have that before. Before, everything was binary, right? It wasn't balanced, but everything, you only had 2. So our data structure is going to be a little bit different on this. Okay. All right, let me let her finish.
And so what it allows us to do is very quick lookups of a particular kind. So for example, suppose we use this try to store this very small version of the English language. We could use it to say, hey, are there any words that start with CAR? Yes, there are. There's car, that's actually a complete word, but there's also card. So car is also a prefix. So it allows us to do very fast lookups. So let's talk briefly about the implementation of it. So we're going to need a class node, and then rather than having, as we would in a binary search tree, a pointer to the left and right node, instead we have some sort of either array of all the children, or more likely some sort of lookup table that maps from a character to that node. So we can immediately say, do you have a child that is an A? Great, give me that immediately. Additionally, we need to understand not just, is there do you have an R as a child, an R node as a child, but is that actually a complete word or is it just a prefix? And so in addition to each node having a mapping of from character to node, each node also has some sort of flag in it called something like is complete word that represents, is that a complete word or not? We see tries in a lot of problems. So if you're in an interview and you get a question that has some sort of word validation to it, so, check if this is, walk through this table and find all the, walk through this Scrabble board and find all the words, or given this list of strings, find all celebrity names. So when you see something that has some sort of word list validation, think about whether or not a try might be useful. There's one optimization that often comes up in try problems. Suppose you have a situation where a user was typing a word, and as soon as the word became clearly it was going to be an invalid word, you want to say underline it. So someone types C, and you say, yes, that is in fact potentially going to be a valid word. And then someone types CA, okay, great, we're looking good. Now they type CAL, yes, okay, there's words that start with CAL. Now they type CALP, oops, no, that's an error. So that's a good place to use a try. Now the way that I've explained try so far, you would do each of these lookups from scratch. You'd say, is there a C? Is a valid prefix? Yes, there is. And then you do, is CA a valid prefix? And you start from scratch over at the root. Now in a lot of cases though, we actually want these calls to kind of build on each other. So one thing we can do with our try is we can keep state in various ways. So when we look up, is C a valid prefix? We actually store where we are in the tree. So when the user types the very next character in A, we just look immediately, is A a child rather of C, so that last lookup, rather than starting from scratch. And there's different ways you can actually implement that. One way you can do it is to actually keep state within the try. Another way you could do that is actually return the node back to the caller. So when I say, is C a valid prefix? I get not only that it's a valid prefix, but I also get information that gives me exact reference to that node. Then, rather than starting from the root and saying, is CA a valid prefix? I just ask, is A a child of C? And then I ask, is L a child of the CA? Et cetera, et cetera. So again, tries are not something that you would spend a lot of time in algorithms classes or in algorithms textbook. And so they're unfamiliar to some people. But it's a very, very common data structure for a lot of interview questions. So keep an eye out for that construct or that frame of a problem that says something about validation of words, because that's often where we're going to want to use a try. So now that you've understood the basics of the try, why don't you try applying this to a new problem? Good luck.
Okay. There's a link to that saved on your Canvas page. All right. Let's see here. Suffix tries. Okay. Now, before we get too much into these slides here, I actually want to talk about something called depth first search. Okay, and here the original author of these slides, he starts talking about depth first search as though you know what it is, and I'm assuming that most of you do not know what a depth first search is. So we're going to spend about 10 minutes. Most likely, you may need to develop an algorithm for the upcoming assignments. I'm not sure, to be honest with you, whether or not you're going to need to implement a depth first search, but you need to at least understand the concept and what they are. You may not necessarily need to implement one. Okay.
Hello and welcome. My name is William, and today we're moving on to talking about the depth first search algorithm, which plays a central role in several graph theory algorithms. So what is a depth first search? A depth first search is a core algorithm in graph theory that allows you to explore nodes and edges of a graph. So it's a form of traversal algorithm. The nice thing about a depth first search is that it's really easy to code, and it runs in a time complexity of big O of V plus E, that is vertices plus edges, which is directly proportional to the size of your graph. By itself, a depth first search isn't all that useful, but when augmented to perform other tasks, such as count connected components, determine connectivity between nodes, or find bridges and articulation points, the depth first search algorithm really shines. So let's look at an example. As the name suggests, a depth first search plunges depth first into a graph without regard for which edge it selects next, until it cannot go any further, at which point it backtracks and continues its exploration. So a depth first search has to start on a node, and I'm going to start our depth first search on node 0. And now we arbitrarily pick a node to go to. So from node 0, we're going to go to node 9. Then from node 9, we have one choice, which is to go to node 8. At node 8, arbitrarily pick an edge. So we're going to go outwards to node 7. Node 7, we have plenty of edges to choose from. So let's go to node 10 to node 11, and 11 to 7. So we don't want to revisit already visited nodes or nodes that are currently being visited. So we have to backtrack. To indicate backtracking, I'm going to label edges and nodes as gray. So backtrack all the way back to node 7. So we're not finished exploring node 7 because there are still edges to be picked. So I'm going to go to node 3. At node 3, I'm going to go to node 2. Node 2 is a dead end, so we backtrack, then go to node 4. Node 4 is also a dead end, so backtrack from node 4 back to node 3, then pick node 3's last edge to go to node 5, 5 to 6, and 6 to 7. Can't go to 7 because we're visiting 7 currently, so backtrack all the way back to node 8. From node 8, we still need to visit its last edge, which goes to node 1. Node 1 back to node 0. We can't go to node 0 because we're currently exploring it. Then backtrack all the way to 0, which completes our depth first search traversal of this graph. So this was one particular depth first search traversal, but as you saw, it could have gone a lot of different ways. So now let's look at some pseudocode for this depth first search to get a deeper understanding of how it works. The first thing we'll need to do is initialize these three variables, which are n, the number of nodes in our graph, g, the adjacency list representing the graph, and visited, a Boolean array containing true or false at index I, depending on whether or not node I has been visited. In the beginning, this array should have all false values because we have not visited any nodes in the graph. Once that is set up, at the bottom, I define our starting node to be node 0 and then call the depth first search method to do the exploration. The depth first search itself has one argument, the current node we are at, which I have conveniently named at. This method is recursive, so I check the base case which is whether we have already visited this node. If so, we have no business here and can return. Otherwise, let's visit this node by marking it as true and exploring all of its neighbors. To explore all the neighbors of the node, reach into the adjacency list and pull out all the neighbors of this node and explore them depth first by looping over each and recursively calling the depth first search method. And that's all a depth first search really is in a nutshell. Let's look at another simple use case for a depth first search. I want to discuss finding connected components in a graph. First, let's understand what we mean by connected component. Sometimes a graph is split into multiple disjoint components, and it's useful to be able to identify and count these components. One way to identify these components might be to color them so we can tell them apart. But what does coloring nodes really mean to a computer? Coloring nodes is equivalent to labeling each node in a component with the same ID value. For example, every node in the purple component gets an ID of 1, and every node in the green component gets an ID of 3. We can use a depth first search to identify components this way. First, make sure all the nodes are labeled from 0 to n non-inclusive, where n is the number of nodes. The basic algorithm is to start a depth first search at every node, except if that node has already been visited, and mark all reachable nodes as being part of the same component using the same ID. So if we start at node 0, then we do a depth first search here, and then every node in this component gets an ID of 0. So we go to 8, give it an ID of 0. 14 gets 0. 13, also label it with a 0, then backtrack like you do a depth first search, then explore node 4, give it an ID of 0, and then finish exploring that component, and then move on to the next node in order. So go to node 1 next. Then node 1, start a depth first search there. So go to node 5, label it with a 1. 5 goes to 17, label it with a 1. Backtrack, go to 16, also label it with a 1. We're finished exploring this component. Then we would go on to node 2, wherever node 2 is, then explore that component. Then node 3, explore node 3's component, unless node 3 has already been visited, and so on. So we do this for every component, and eventually we get to label all the components, and we used a depth first search to do that. Awesome, so that's how we find connected components using a depth first search. Now let's look at some pseudocode for how we do this. First, we'll need a couple of things. We'll need everything from the previous code we looked at, so n, the number of nodes in our graph, g, our adjacency list, and our visited array. But additionally, we'll also need a variable called count that tracks the number of connected components and components, an integer array that holds the integer value of which component a node belongs to. Inside the find components method, we loop over every node and check if the current node has been visited or not, and then execute some logic. This depth first search variant differs slightly from the previous in that we execute a depth first search for every unvisited node. When we actually do the depth first search, we visit nodes and mark them as visited. So we never revisit the same node more than once. We either skip over a node because it's been visited in this for loop, or start a depth first search there. If we start a new depth first search, we increment the count variable and keep track of how many depth first searches we have done.
So you want to be a software engineer at Google? Go to algoexpert.com.
Give it a second.
Inside the depth first search method itself, the two things we do are mark the current node as visited and set the current node to be part of the component equal to the value of count. Then simply iterate over every neighboring node that has not yet been visited and call the depth first search method to explore them as well. Back inside the find components method, simply return the number of components and the components array that contains the information about which component each node belongs to. So we've covered two of the things you can use the depth first search for, doing a simple traversal and determining connected components. But we can augment a depth first search to do so much more, such as computer graphs minimum spanning tree, detect and find cycles in a graph, check if a graph is bipartite, find strongly connected components, topologically sort your graph, find bridges and articulation points, find augmenting paths in a flow network, generate mazes, and many, many more applications. So a depth first search is super versatile and can be extended to do a whole ton of things. Thank you for watching. Next video, I should be talking about the breadth first search algorithm. Stay tuned and subscribe for more mathematics and computer science videos. Cheers.
Okay, folks, so that video as well is also posted in your
Hello.
in Canvas. Okay. All right. Okay, so if we go ahead and open up our next slide, it should be slide 2. Again, we're in the tries and suffix trees section. Looking here, you know, we're going to be covering tries, suffix trees. Let's see, suffix arrays. Let's see, least common. Oh, what's the P? LCP array. Okay, we'll cover that. I got to brief up on that more. Which are more, these are more space efficient way of coding suffix trees. And then the following week, or at some point, we're going to get into something called SAIS algorithm, quickly builds these suffix trees and suffix arrays. It's probably the, you know, according to the author here, the most beautiful divide and conquer algorithm ever invented. Okay, so I'm looking forward to getting into this guy. Okay, tries and Patricia trees, tries. Okay, so here he's talking about, you know, if you type in Google, right? You guys start typing, all of a sudden this little box pops up and you got all these alternative or all these previously searched words, right? So, you know, has anybody here ever wondered how that's done? I mean, that's kind of cool if you think about it, right? There's many times when I'm doing a Google search, I don't even know how to ask the question, right? You know, you start typing and then you get some, you know, auto-filled options here. Okay. So the autocomplete problem, that's what he's defined here. So let's see if we can interpret this in a way where we can understand it. So here we have a series of text strings, right? That's these guys here on the bottom, right? That's all these guys here. We have a series of text strings that have a total length of m. Okay, we have a pattern, a search pattern called P that has a length of n, and the goal is to find all text strings that start with P, right? So it's going back. How many of these text strings, do we get that actually start with what he's typed here? Of course, when he started typing, he started typing with the W. Well, who knows? This thing pops up. Let's even do it. Let's do that. We go to Google. I start typing W. Now, this actually is got a lot more to do with what I've typed lately, right? Let's see here. What was the actual thing he typed in? What is the cutest animal? All right. So here's WH, what dinosaur has 500 teeth? I promise you, I've never asked the question. I don't care how many teeth a dinosaur has. They're all bad, right? I don't want to be eaten by a dinosaur. Let's see here. What was the thing? The question again was, what is the cutest animal? All right. So what is, as you see this, it's starting to populate here, right? So the question is, how is this done so quickly? So the goal is to find all these strings. If we do just a single query, then we can solve this pretty easily. You just scan over all the strings, all the possible strings, and see which ones start with P, right? Well, I mean, what strings are they? Let's say you have a dictionary of or a text file that has 10,000 sentences in it, right? Maybe it's a book, maybe it's a small book or something. And you have all those sentences saved into a text file. So let's see here. Let me do some drawing. I still need to find my Wacom glove. All right. So let's say we have our book, our textbook. Let's see if I can draw it off to the side here. So we have our textbook with all its, our file with all its text, okay? And what he's saying here is, well, let's scan all of these to see, let's say we have, from line 1 through 10,000. Okay. Well, I mean, that's a linear search, right? And when you're looking for just P, yeah, nope, that's not it. That's not one. Or maybe this one does have, maybe that one has, now you're just looking for one character. Well, that's not too bad, right? P, not a P, not a P, okay? So here we would, after we've done this search of 10,000, okay, we would return 3 sentences, whatever this is, right? Let's see, pigs like mud. Pizza is awesome. And parties are illegal. Oh, that's right, you guys. California, yeah. All right, so anyways, hey guys, listen, and I'm being serious here. I know I was joking just now, but has anybody here heard anything about campuses opening up 50% of the classes for the fall? Have you guys gotten any information about that?
No.
I'm sorry, I can't hear you. No?
They
No.
usually would send out an email, but I haven't seen an email yet.
Okay, man, I can barely hear you guys. Let's see. All right, so anyways, I'm just, I'm just informing you, right, that the administration is telling faculty that we have to do 50% of our classes on campus next fall. Faculty are saying shove it, right? It's too risky. So anyways, the reason I bring it up is not for you guys to get involved or upset or anything. I'm just letting you know there is talk about it. Me personally, I have no intention. I'll not go back to campus in the fall. Okay. Just it's going to be interesting. This upcoming fall is going to be interesting. And I was just curious if you guys had heard anything or, so just don't be surprised if if there's some sort of discussions or whatever that you guys are invited to later about whether or not you want to. Okay. All right, let's get back to the task at hand here. So as you can see, right, I mean, that's not too bad when you're looking for one word. Just scan over all the, let's see, well, first of all, well, that's if the string P only has one word, one letter in it, P. But what if my string had, 2 letters in it? What if my string had PI? Okay, well, you would have to scroll through and find, all right, you know, and go one at a time. Okay, so the length of my string, which is n, okay, we'd have to go through potentially worst case scenario, right? Every one of these works, every one of these fits n times m, which is the number of strings I have. Okay, and that could start to take a little bit of time, especially if we have long words. Okay. So the question is, if we have a set of fixed text strings in varying patterns, can we speed this up? So a naive solution. So here again, this is the same thing. We're just going through, looking to see, we go through and we look to see one at a time if these characters, you know, and since every one of these has a match or to some point for the A, right? Okay. Yep. We compare here, but then we find out that once that user types in the letter E, this guy here now falls off, right? And then of course, here's a match, that's good. Here's another match, so this one would stay on. But look how many times we're having to do these comparisons. We have to start all over from scratch, right? We have to start at the very beginning again and come all the way down through here, right? And the same thing here, we got to start all the way back over again. But see, if these guys were hooked to one of those tries, like you saw earlier, we don't have to, you know, we can save the effort of resetting. So for example, we would, you know, after we've done, you know, after we've gone to this one, even though it didn't match, this guy would have a branch that had an E on it. Oh, you know what? That's a match. This guy here would also have a branch, and then this E would have a branch, you know, one for the A. Well, let's see here. Actually, yeah, the E would have a branch all the way through. The E has another branch for the L. And of course, each of these have branches as well. Let's see. Let's see here. You know, could we try and build this try? Can we try to, let's see if we can build this try out by hand. Okay, so when I could, all right, give me a moment here. Well, bear with me, guys. Professor B's dropped his pen. Okay, let's see if we can get this thing to draw out for us. And we'll make it a nice green color. All right, so we start off with the root. And the letter A. And we can take N. Since A only has one, you know, we can just go straight down to the N. By the way, in finite automata, if you ever see one of these, like a double circle, that means that's the end of a state, right? If it's a single, it means that it's not completed, right? So if I wanted to show, if I wanted to do some kind of string like ANT, right, I could go A, N, T, and then end it, right? That's it. Okay. All right. And you guys will get finite automata later on. Let's see here. But this is almost, actually, this is the same thing. It's almost exactly the same thing here. Okay. So on the N, we still would only have one branch for the T. But now in the T, we would have two branches, right? We have an E and an I. let's put the E over on this side here. And the I over here. Now, you would also have a asterisk here, right, for the T. That's an E. And since, you know, E is also complete, that would also have a asterisk here. Okay. And there's and T. And then over here, you'd also have the I, but the I is not complete. So the I would then have a Q. You'd then have a U. You'd then have an E. And then you'd have your end state. Okay. So now over here, from the E, you have an A, a T, an E, and an R. And then you'd have your end state. You have the EL. End state. And then you'd have your EQ, or I'm sorry, no, that's it, right? There's ant. Oh, we got two E's. Ant eater, antelope. Then you've got antique. Now, I know it's hard to read this, but I'm hoping you guys can see. You know, these aren't that hard to build out. Okay. All right, so that is how a trie might look to map these. And so whenever you're going through and trying to, you know, find these matches quickly, as you're traversing these, I don't have to go backwards. Okay, here, so for anti, I come to here, and then I know, so you explore all possible edges. This is called an edge, guys. A line that connects two nodes is called an edge, right? And then a vertices. What's a vertices? We have edges and vertices. So if that's an edge, these are vertices. Okay. So we'd come down and nope, that's not it. Let me put a. Okay, so we can line this guy here out. Boom. Nope, that's not a match. But this one here, okay, this one is a match. It doesn't even have to be a complete word, by the way. It just has to match this guy. So that's a match there, okay? And then we try this. So this one here's been checked. These have all been checked, right? Now we're gonna go down this line, and you would print the entire, you would print the entire string, okay? Not just little substrings here. So this one here would be a match, and it would just go down through here, you know, all of these. It doesn't have to go backwards, okay? And then of course the same thing for the, for the, oh my goodness. Same thing for that one, and this one, okay? So that's kind of how that would show up. Okay. All right, any questions on this trie, on this example? Okay. So now what he's talking about here, he's saying that, if we use just a traditional array and we go through and loop through this stuff, I mean, there's a lot of times, there's a lot of rework. And so what he was just saying here is, this is just another, just another layout. And you see these little end states here, right? Those double lines mean that's an end or a possible end. Each edge is labeled with a character. Some nodes are marked as representing words. By convention, children are stored in sorted order. Pre-order traversal of the trie prints all words in sorted order. Okay. Now, in order to do this, then what we would do would be, to do a depth first search. That's why I showed you guys that video, to find all words that are rooted here, right? Rooted here, because we're looking for anti. Well, the rooted here is, this one. Root means you have a null, okay? Or you have the, the end state. And so that would be these words of anti, anter, and then anti, anteater, and then antelope. So here he's saying that we fell off the tree. Why? Because that I is not in here. So we fall off, so there are no matches. You don't go any farther. Okay, so here he says the total length is M for the number of strings we have, and the length of our pattern is N. How long does it take to build our trie? It says here, ignoring the size of the alphabet, the runtime is big O of M, so it should be how long does it take to check the pattern is a prefix of any string. The claim is that it's big O of N. How long does it take to find all the text patterns? Well, he's saying that's a trickier question, because it depends, right? It depends on how many matches there are. Let's see here. Question 1, in what format do we want our matches? Option 1, just print out all the matches, search for the prefix as usual, do a depth first search, recording the letters seen on each branch to rebuild all the words. We can upper bound runtime by the number of strings that we have, or the number of strings, and basically it's the number of characters in all of our strings combined, right? So if you had if you had 10,000 characters in a text file, right, that that's what that M is. It's not just the number of sentences, it's the number of sentences and their corresponding links added together, right? Or just actually the string lengths of each sentence. That's probably a better way to put it. And then of course, N is the length of the string that you're trying to match. He says here, but it's hard to say much more than that, because we don't know, right? It just depends. There may not be any matches, okay? It just really depends. We could upper bound this expression as big O of M if we'd like, but he's going to show the cost. He likes showing both costs here, okay? There's another option, is to assume each text string has some numeric ID, and we want all matching IDs. Ideally, we'd like a time complexity of the length of the string that we're trying to match plus the number of possible matches, right? He says our current depth first search can't achieve this. The lengths of the strings matter. He says, can we do better? Okay. So here he's showing an example, right? He's reset the problem. Okay, here are our strings. Now, let's see here, the $ symbol is called the sentinel or end marker. Okay, it's a special character that can only appear at the ends of words. Think like the null terminator, right? By convention, the sentinel $ precedes all other characters. He says it really is like a null terminator. Well, why not use a null terminator, right? Nodes now fall into one of two classes. Leaf nodes correspond to words in the trie. Okay, that's the purple. That means that there was a match to what you were trying to look for. I'm sorry, no. It means that these are the words that are in the trie, the infrastructure of the trie itself. So here we see we've got 5 different words. And then the internal nodes correspond to the routing, right? This just shows the pathway, right? He says a node is a silly node if it is a non-root node that has only one child. Okay. Let's see here. A node is a silly node if it's non-root node, say this guy right here. Let's say we're looking at this guy here. A node is if it is a non-root node. Okay, so here's my root node. So I can't, so A is not a silly, whoops. Okay, so A would not be a silly node because it is a root. Okay, so this guy here, well, only has one child. Yeah, he actually does only have one child. So AN is a silly node. Even AN, let's see, ANT is not. Okay. So basically saying, it's like saying, you know, we're not worried about, or silly nodes represent the letters whenever they don't complete a full word. Okay. A Patricia trie is a trie where silly nodes are merged into their parents. Okay, let's see here. That means that the labeling of the edge, we don't even look at the nodes right in between, even though there's differences here. What's happened is that these have been merged together. Okay, so this is more like a string that this particular edge would represent. Okay, why? Because now we have four words: ant, auntie. Okay. Let's see here. Oh yeah, there. So here's the $sign for this, for ant, you know, for anteater. Here's the $sign for auntie. Here's the $sign for ant, and here's the $sign that shows me the end of antelopes, and over here is antiques. Okay, so that's a Patricia trie. This is a, you know, this is just a general trie, I guess you could call it. Your traditional trie. Here, that's your traditional trie. These are considered silly nodes. Okay, and so we want to cut to the chase and just have a, you know, merge these nodes together, and you know, into one node. So for example, let's see here. That would be the root. The word ant. Well, I mean, it's really the edge that we're talking about here. Okay. But notice, so how many nodes got removed? So we removed 1, 2, 3 here, right? We removed those 3. We removed, let's see, eater. Let's go back. Yeah, we removed this one. We removed all these nodes, and we just combined them. And the same here. We removed all these nodes and combined them. So that's a Patricia trie. Okay, that's a better look at it. So observation number 1, every internal node in a Patricia trie, except possibly the root, has 2 or more children. Every internal node. So let's see here. Well, these are the nodes. Okay, so the children of this guy here. This is the children of this guy. This one, well, that's 1, but this here makes the 2, right? So even this node with 1 letter right here has 2, because of the $sign here. You see? Okay. And then this guy here obviously has more than 2. This one has 2 or more. This T has 2, right? That counts as a child, and so does that count as a child. And so does this. That counts as a child too. So that's kind of interesting to see that, all right, each of these internal nodes have 2 or more children. Observation number 2 is leaves correspond to words. Internal nodes are therefore for routing purposes. Okay. So here's a theorem. He says the number of nodes in a Patricia trie with K words, right? 1, 2, 3, 4, 5 is always big O of K, regardless of what those words are. Okay, because you're doing one jump. It's only one jump. You know, because each of these edges represent a series of characters that are building words. There are K leaves, 1 per word in the trie, as you guys saw. Think of this as a forest of K different trees, right? So each of these is a different tree. A different trie. I'm sorry, different trie. Different trees. Okay. Adding an internal node merges 2 or more trees together, decreasing the number of trees by at least 1. Okay. Adding the root might not decrease the number of trees, but there's only 1 root. All right. We're not going to worry about the proof. All right, but he is making a claim. So if each leaf in a Patricia trie is annotated with the index of the word it comes from, all strings start with a given prefix can be found in big O of the length of the string we're looking for plus the number of matches that we have, which is Z. So he's asking, so if you look, right? Let's say we're looking, well, he does, let's see, he's going to show an example here. Okay, use a 2-phase search algorithm. Character aware, read the prefix to search for, matching the characters as you walk down the Patricia trie. Character blind, if you didn't walk off the trie, walk off means that you, basically you're still on the trie, right? So each of these are their own little trie, own little mini tries. So what he's saying is that if you didn't walk off of this particular trie here, for example, then your current point, let's see, do a depth first search below your current point to find all the leaves, ignoring the strings on the edges. Okay, let's see here. Documentation, those runtimes hide the effect of the alphabet size. Take some time to evaluate those trade-offs. Okay, it's right now 4 o'clock, guys. I don't want to get too far into this because I know you guys have the upcoming assignments. Now, does anybody have any questions over tries, Patricia tries, or the depth search algorithm that we watched on video? Okay. All right, so let me do this. Let's close this down, and I'm currently I'm getting ready to build out the problem, the problem set, right? The paired one on Gradescope, right? The only thing you turn in on Canvas for that problem is a screenshot of the program running, right? But your code, and then you've got to tell me whose directory those problem sets are in. I'm assuming most of you are going to use that. I'm assuming most of you are going to do the one that matches the number of boxes, right? Let's see here. That was this guy here. I'm assuming some of you are going to do the skyline problem, or the area minimum query problem. Okay. Obviously, you got the hybrid, which we spoke about before. On constant factors. Right now, I didn't cover the Fisher-Hune range minimum query structure, but there is a paper. You're welcome to read it. All right. So let's see here. Due March the 4th. Not due March the 4th. It's strange that says March the 4th. Okay. All right, guys. That's basically it for today. So let me ask you this. Let's have a look here. I want to see how we're doing on teaming up on these problem sets. Man, you guys haven't even teamed up. You know what? Then I'm not moving that assignment. That assignment's staying where it is. Okay. So let's jump into this guy here. Okay, so the problem set 1 is due March the 2nd, and along with your individual assessment 1, right? So you basically you guys got 7 days, 8 days, right? Because you got a full day, you don't have to turn it in until midnight. I will have the grade scope essay questions posted by next class, and then we're going to pick up with the rest of our discussion. We're going to pick up suffix trees. Okay, I'm seeing some chat. Let's see what we got. No, you don't have to implement all 4 of them. Okay, you pick one. You guys, Nima and Patrick, you only have to pick one on that problem set. Okay. Can I get a, let's see, where is mine? Let me stop sharing. Can I get a thumbs up? Everybody understands in the problem set, you only pick one. You guys pick one, right? It's mercy time. It's time to have mercy on you and me both. Okay. I'm going to tell you, I'm absolutely looking forward to doing these tries. I can't wait, because that just seems so fun to be able to do those, do those word problems. If you ever get your master's degree, guys, you will definitely see that problem again. Okay, I had that, and I had that depth first search as my part of my master's degree program. So you guys at a community college, you can say that Professor B is giving us master's degree problems, right? Oh man, he's so mean to us. Okay. But they are very interesting. They are very interesting. Okay, now for that depth first search, guys, the code's there, right? You don't have to generate that code on your own. And the same thing for these tries. Okay, there's code out there. I know it, you know it. So just let's get some experience with these data structures, and then you guys are going to do well and be very, very, I think you're going to be very successful, right? I kind of got a feeling that this, my goal is that you guys will smoke any of the other data structure students. If you were to be, had some kind of job interview or whatever, that you would be able to just crush the discussion, right? Because I can promise you, they're not covering tries, or suffix trees in the other classes. Okay, guys, that's it for me. Now you still got lab. I have office hours. It's going to start at 5:30. I'm going to have my dinner. Okay. But that is it for today. So you can go ahead and stop recording. And now I can't help you with writing your code. That's just, that's just a no-no.